resume recording. Yes. Now I should be recording. So we just introduced matrix A and their entries. Okay. So in general, a matrix A of size n by n is in the form of, you guys still remember how do we write a matrix A in general? So A m by n could be a big rectangular arrays of items, right? Here you can put m by n, again, indicating its size. First entry will be ace of
1,
1, and then ace of 1, 2. First row, second column, right? And keep going until it gets to the last entry will be ace of 1. I'm waiting for you guys. Ace of 1 what? N. Because there are n columns, right? Number of columns. Okay, second row, same. A to 1, A to 2, ace of 2n, and then keep going until you get to the last row. So there are m rows, right? So number of rows, m rows. The last entry will be ace of m1, ace of m2, and the last entry here will be ace of mn. Yes, ace of m. Ace of mn. Okay. This is a quick way to express the matrix A with its elements. Okay. So we count rows from the top to the bottom, right? That's the order of your counting. So top down, and then we count the columns from left to right. Ace of ij is the entry of matrix A in where? When you say ace of ij, let me see. When you see ace of ij, row and j column, right? So if I put a matrix here, you may have supposed to be, this is ith row, and here is supposed to be j column. The intersection will be ace of ij. This is pretty straightforward, right?
Yeah.
Okay. Page 2. Let's see. So example 1. Let matrix A be given as 3, 2, 1, 0, 5, 9. Then ace of 2, 3 equals what?
9.
Yeah, it's second row, third column, so that's going to be 9. Ace of 1, 2 would be 2. We can take out one row column, row vector, right? This is row vector. Row vector, row 2, R2 is row 2. So row 2 will just be 0, 5, 9. So you pull out 0, 5, 9. Okay. You also do column vector, right? Column C3. What does a C3 mean?
1, 9. Oh, well, it's the third column.
Yeah, third column, so it'll be just 1, 9. Very self-evident, right? Pretty easy. Spectral matrix, there are 2 types of spectral matrix we want to talk about in this differential equation, system of differential equations. We want to talk about a spectral matrix of identity of n. So I of n is identity matrix. The size is, when you see this n, it means it is size n by n, right?
Mm-hmm.
What's special about our identity matrix?
It's all ones.
All ones.
And it's the equivalent of 1 in the matrix world.
Yeah, it's only have the ones on the diagonal, right? Diagonal. Everything else is going to be zeros. 0, 0, everywhere. Everywhere, 0.
I have a question, Dr. Wu.
Donovan?
The arrow above the C and R, is that just notation or does that determine a direction?
Good question. So this arrow, a lot of folks forgot to write it. This arrow is indicating this is actually a vector, okay? Guys, remember when you write vector, you do U vector,
Yep.
V vector, right? So same thing here. This row, the second row is considered to be a row vector. So it's R2, so R2 second row, and you put a arrow sign just on top of it to show this is a vector, okay? Same thing for the C3. C3 is a column containing 2 elements. So this is a vector, column vector. We call these two as row vector and column vector, okay? Is that good so far?
Mm-hmm.
All right, next we want to talk about zero matrix. You guys recall what's zero matrix?
What it sounds like.
Yeah, it's all zeros.
All zeros.
So n by n, right? N rows and columns, all zeros. Okay. No, that's a too big zero. So 0, 0, all the zeros. 0, 0, 0, 0, zeros. Okay, I do want to emphasize identity matrix and zero matrix. There are something different between these two. For identity matrix, it has all the ones on the diagonal. Identity matrix has to be square matrix, right? Identity. Zero matrix can be square shape. It could be a rectangular shape. It doesn't have to be square matrix. I mean, the number of rows doesn't have to be the same as number of columns. Okay, now can you guys recall what's I4? Can you write down I4?
Of which matrix?
Example 2.
1 0 0 0 next row 0 1
0 1 0 0 0 0 1 0. Thank you, Bertrand. 0 0 0 1. Right. Zero matrix of 3 by 2.
This 0 is just 2
6 of those. Right.
column.
So three rows and 2 columns, all zeros. Okay. Easy. Next, let's talk about how do you do operations of matrices, right? So matrix operation. First of all, the easiest operation you can do is you can transpose a matrix, okay? If matrix A is n by n, okay, n by n, then the transpose of A, which is simply denoted by A transpose. Or do you guys recall another notation for transpose? Any other note?
when you
Transpose is when you flip the row in the column, isn't it?
yeah
Mm-hmm.
so it would go 3 0 and then the next row 2 5 and the next row 1 9.
You guys are way ahead of me.
Oh.
I'm talking about what is the other notation for A transpose that you might see?
Widgets, you're a machine.
I don't remember.
Anybody recall another notation? A prime.
A prime.
Yeah, sometimes you see A prime. A prime. Okay. That's the same thing as A transpose. So certain book would use A prime for transpose. Okay. But anyway, you guys remember it correct. So A transpose basically is interchanging the rows and columns of the matrix A, right? So the first row turns to first column and second row turns to second column for the transpose. You can also tell here the notation. If it's entries A sub ij, then in transpose is A sub ji, and the size needs to be changed. So here we go. The matrix A 3 2 1 0 5 9 and A transpose would be.
What Bridget said.
Yeah, what Bridget just said. 3 2 1 goes downward, and 0 5 9 goes downward too. Right? This is easy enough. Good. Originally it's 2 by 3. Now it's 3 by 2. Okay, 3 by 2. The first row goes to first column. Okay, now let's move on to page 3. Next is about equivalence between two matrices, addition and scalar multiplication of matrices. Okay. Quick recap. If you have two matrices, okay, matrix A and a matrix B, they happen to be of the same size, then how do we make sure these two are exactly the same matrix?
The N and M have to match.
Yeah, and they already match. Okay. Guys, other than the size matches, what else that we gotta make sure?
Direction?
Determinant.
Direction? What direction?
I don't know, matrix. I don't know.
Does it have to do with the determinant?
Yeah.
No. You guys are overthinking. Okay.
Linearity.
Don't it need to have the same M and N?
You already have the same M and N.
Well, then I'm assuming they just need the same points.
Same elements. They must have exactly the same elements.
Number.
Right, at I and j. So a sub ij should equals b sub ij for all I and j. Right? For each position, they should have exactly the same entries. Good?
Yeah.
Yep. If C is a scalar, okay, scalar means a number, then we can multiply a matrix by a number, right? How do we do the multiplication?
You just multiply every element.
Multiply everything, right? Every element by the C. So CA would be a matrix of the same size, n by n, whose entries are scalar C times each entry, a sub ij. How about addition and subtraction? How do we add two matrices? How do we subtract two matrices?
The elements have to have the same IJ.
So you just add the corresponding elements, but the result will be the matrix of the same size, right? Still n by n matrix, whose entries are a sub ij plus b sub ij for a plus b. For a minus b, we have the same size, and then you just subtract the corresponding elements. What do we need to pay attention when we are doing all these operations?
Making sure they have the same size.
Correct. So A and B need to be same size, right? For all of these operations. Equivalency, scalar multiplication, and not scalar multiplication, they don't have to, and for addition and subtraction. Okay, let's finish page 3 real quick. We have these two matrices given, okay, matrix A and a matrix B. What's going to be matrix 2A and what's going to be matrix A minus 2B? 2A should be quick, right?
6, 4, 2, 0, 10, 18.
Yep, 0, 10, 18. Okay, this is still 2 by 3 matrix. How about the second? A minus 2B.
3 plus 6.
3 plus 6, yeah.
I'm gonna do this. I'm gonna write matrix
-2.
A here. So matrix A minus 2B. So I'm first going to calculate 2B. How's that? Would that be easier?
Yeah.
2B. So it'd be -6, 4, -2, A, 0, 12. And then I would just do A minus 2B, right? Just do the subtraction. Okay, here we go. We have 9, -2, 3. What's next row?
-8.
-8,
5.
5,
-3.
-3. Okay. Pretty easy. The last one, what's A plus B transpose?
Gotta add them up first.
Yep, first of all, let's do A plus B. So
0,
A plus B is 0,
0,
4, 0. So you just add, right? Add the corresponding elements, 0, 4, 0. And next will be
4, 5,
4, 5, 15. Correct?
Yep.
For A plus B. Therefore, A plus B transpose will just be 0, 4, 0. Okay, first row turns to first column. 4, 5, 15. Second row turns to second column. Everything good?
yes,
Kind of like quick review of linear algebra, right? All right, next is page 4. Comes to the matrix multiplication. This is the part that you guys would have spent most of the time on, right? Anybody recall what is the requirement for us to do matrix multiplication?
and
Oh, I'm sorry, go ahead.
To be, the two ones in the middle, the n and the n have to match, not the outside parts.
Yeah, So the number of column for matrix A should match the number of row for matrix B in order to perform A times B, right? So for A times B matrix multiplication, number of columns of A should match the number of rows of matrix B. Okay. Only when these two sizes match, then we can perform matrix multiplication. And this is the product. This is the product of matrix multiplication. This product would be a matrix of a size that's different from A or B a lot of times. So that would be M, which is remaining, M, and P. So in general, we say M by N. Multiply with n by p. For these two matrices, the n would be canceled out. We'll just get m by p. Right? And how do we actually do the calculation of those entries? You guys still recall?
multiply each. So first row of A multiply by first column of B.
First row multiplied by
to get Q11.
Yeah, Q11, and then first row multiplied by second column, forget it, Q12, right? In general. So in general, Q's of ij, which is in ith row and j's column of the product A, B, that equals 2. What does this notation mean?
K goes from 1 to n.
What does the
Summation of
sigma mean?
all.
Yes. So sum of, right? Sum of the product, right? Sum of the products of the ith row of A and jth column of B. Right? So ith row of A and jth column of B, when you multiply, when you add these two columns, and when you multiply these two columns, you get the ith row and jth entry of the final product AB. This sounds a bit abstract, but we'll see examples that hopefully can fresh back your memory. First of all, let's work on example 4. We had A, B, C, D, E, 5 matrices. Okay, well, we didn't use all the, you just need to use A, B, C, D. Let's see, let's determine whether the following matrices exist or not. which means can you perform such multiplication? Yes or no? First one, can I do B multiplied by A?
No.
No.
B is 4 by 5, A is 4 by 5. The number in the middle doesn't match, right? So no. Can I do A times B?
Nope.
No.
4 by 5, 4 by 5. No. Okay. Can I do AC plus D?
Yeah.
Yep.
Okay. So A is 4 by 5. C is 5 by 2. Yes. So this turns out to be 4 by 2, right? Matrix D is 4 by 2. So I can add these two matrices. That is okay. And the sum would be 4 by 2 matrix, right? Good? Okay. Next, let's do page 5. We're still in the reviewing process here. Let matrix A be 1, 2, 0, 1, 5, negative 1. Matrix B be negative 1, 3, 2, 4. Find the following matrix if it exists. So first of all, you need to confirm if this one exists. If yes, then go ahead and find it. Matrix, can I do A times B first of all?
Yep.
Okay, A is 3 by 2, B is 2 by 2. Yes, you can get a 3 by 2 matrix, right? So it should be 3 by 2. Okay, 3 by 2. The first entry. So there should be 6 entries. 1, 2, 3, 4, 5, 6. First entry will be in the first row, first column. Then we should take first row of matrix A, first column of matrix B, right? And do the multiplication. You guys recall?
Yep.
We do pairwise multiplication. So 1 times negative 1. So 1 times negative 1 plus
2 times 2.
2 times 2. Yes, so that turns out to be 3, right? Okay. Move on for the second entry. It's in first row, second column. So this time we do first row, second column. Okay. Again, you do pairwise multiplication. So 1 times 3 plus 2 times 4, which gets you 11, right? Okay. And then next will be second row, first column. So we should do second row, first column, okay? 0 times negative 1 plus 1 times 2, which will be 2. I'm just going to do the last one here and then ask you guys to finish the last row here. This entry would be second row, second column. So second row of matrix A, second column of matrix B. We have 0 times 3 plus 1 times 4, which is 4, right? I'm going to ask you guys to finish the last row. What are the entries of the last row? Sorry, can you still see my screen?
And negative 7, 11.
I can't tell. Is that a negative 1 on A?
Yeah, 5, negative 1. Yeah, on the matrix A. Sorry, let me write the matrix A here. Matrix A is 1, 2, 0, 1, 5, negative 1. The first entry here would be third row of matrix A and the first column of matrix B, right?
Yep.
You guys have -5 minus 2. Is that -7?
Yep.
Yeah.
Lastly, we should have third row of matrix A and second column of matrix B. So that's 15 minus 4. That's 11. Right?
Yep.
Okay, good. All right. Can we do B times A?
No.
No.
B is
2 by 2.
B is 2 by 2. A is 3 by 2. So no, right? You can't do B times A. In the end, can we do AB transpose?
Yep.
Yep. This is easy. Okay, so transpose, we'll need to just transpose what we have got over here, right? So 311 will turn to first column. Let me go ahead and just zoom out a little bit. Maybe this will be helpful. Okay, so we should have 311 in the first column, 2, 4 in the second column, -6, 11 in the last column. And this should be a 2 by 3 matrix. Is everything good?
Yeah.
Yeah, questions? No question?
No.
Okay. Let me check with Joshua and Donovan. And also is, let me see, is Jaquan here?
Yes.
Yeah, is everything fine, Jaquan?
Yes.
Joshua and Donovan?
Yep.
Okay, good. Because these are relatively new for you, relatively new for you guys. So I want to make sure that you're fine with this. Okay. So next, let's go to example 6, and then we're going to try to relate our matrix to linear system. Okay, example 6. Example 6 just does a matrix multiply with a column vector. Okay. Can we perform such multiplication?
Yep.
Yep. So matrix C is 2 by 2, and 2, 5 is a column vector, which is 2 by 1, right? So the result should be a 2 by 1 matrix, which is a column vector again. Okay. Same thing. The first entry will be first row times first column. So 2 times 2, which is 4. 1 times 5, that's 5. So 4 plus 5, which is 9. Second entry would be -1, 4 times 2, 5. So I have -2 plus 20, which is 18. Right? So the matrix multiplied by a column vector, you get 9, 18 vector. Is that good?
Yeah, good.
Yeah.
Great. So these are a very quick review of just tiny little bit of stuff from linear algebra. All right, now we're going to try to relate this to the linear system. So item 3, first order linear system. Linear system, you already understand linear system has a few equations involved, and they're all first order. Okay. First order means the higher order derivative you have will just be first order, right? So not we are right. So we can write a first order linear system of ODE as a matrix equation by introducing vector x as x1, x2, blah, 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 up to x of n. So we are introducing this column vector, right? This is a column vector as our x vector, or you can say this is unknown vector. Okay. The vector contains all your unknowns. Let's see. For example 7, we have x1 prime equals 2x1 plus x2, x2 prime equals 3x1 minus x2. What are the unknowns here?
1x2.
Yep, so x1, x2, I can just put this as a x vector, right? We can let x vector containing both x1 and x2. So in that case, how do we write the system as an equation about x vector itself? Let's start with left-hand side. Left-hand side is x1 prime, x2 prime, which is that just the prime of x derivative? So the derivative of x, right, on the left-hand side. And right-hand side, I can say this is 2 times x1. I mean, let's do this. You can say, can I write this as 2, 3, and x vector? What is the best way for us to put them? The other way. The easy way here, guys, will just be write down all the coefficients. Can you just pull out the coefficients? That's the easiest way for us to do. So 2, 1, 3, -1, right? Pulling out all the coefficients and multiply with x1, x2. At the same as 2, 1, 3, -1, this matrix times my x vector. So the equation can just be derivative of this x vector equals to matrix 2, 1, 3, -1 times vector x. Now I have a question. Can someone explain why it's okay for us to write this 2, 1, 3, -1, just pulling out the coefficients and multiply with this x1, x2? Why this is equivalent to what we had originally in this equation?
When we multiply everything, we're still going to get the same.
Correct. So this is related to multiplication, right? Because if you do multiplication, let me change to another color. If I do the multiplication, then you are supposed to be doing first row times first column. Then you have 2x1 plus x2, right? 2x1 plus x2. Make sense? Folks?
Yes.
Same thing for the second row, right? The second row, you do second row times this column. So you have 3x1 minus 1x2, which is the same as what you see in the system. So the easy way will just be take out all the coefficients and write it in a matrix and then multiply it by your vector x containing the unknowns. Okay. Let's move on to the next page. In general, okay, so we're looking at the general case. Let t be the independent variable. Suppose t is the independent variable. And the unknown vector, x vector contains x1, x2, and x of n. How many unknowns exactly?
Again?
Yeah, and unknown variables, right? There are dependent variables, okay, dependent variable. They all depend on variable t. Let's suppose this is a vector valued function. Then a system of ordinary differential equation, okay, this is first order, okay, system of ODEs can be written as x prime equals to some coefficient times x and plus something else. Okay. Kind of like analogy of y prime equals to piece of t times y. Sorry, I didn't mean to write this. Plus q's of t. Right? Have we seen this before? First order differential equation. y prime equals p times y plus q. Here you just put it as x prime equals p times x plus, they change the name as f of t in general. You guys okay?
Yep. Yeah.
It is linear, right? So y and y prime, they're all raised to the first power. Same thing here. X prime and x is raised to the first order. And the highest order of derivative is 1. So first order ODE. And this is a system. We'll see the examples of this P and F in the specific system of equations. But question 1, first note, when this f of t happens to be 0, okay, so if this part happens to be 0, what do we call the system as?
Homogeneous?
Yes, homogeneous. Because there's no other stuff, I mean, like other than first order derivative of y. Or the other way I can explain this would be, let me move this x prime and x on the same side. So you have x prime plus p of t vector x equals to f of t. And suppose this f of t equals to 0. Then you can tell that for this equation, the right-hand side is 0. Therefore, we call this homogeneous system, right? Second note, oh, there's a typo, my bad here. Solutions of all of the solution will be x, right? Solution will be x of t. They should fit the matrix equations. Not solutions of f of t, my bad there. Okay, so next let's try to use what we have just learned and rewrite this following system of equation as a matrix equation. You have x1 prime equals 2t times x1 plus e to the t x2 plus t squared. Second equation is x2 prime equals x1 over t minus x2 plus e to the t. First of all, you need to let a vector x to contain your unknowns, right? What's this vector x?
X1, X2.
X1, X2. Then let's do it step by step. First of all, for the left-hand side, this will just be vector x, its derivative, right? What about the right-hand side? Can we separate the right-hand side into two groups?
Into F matrix of X, into P of T and F matrix, or?
So if you observe, if we observe the right-hand side, some of the part is related to the unknown, x1, x2. Some of the part is not related to the unknown, right? So we can separate them into two groups. The first group will be about these unknown. Second group doesn't have anything to do with the unknown, so I can put them separately. So t squared and e to the t, isolate these from x's. And the first part, which is related to x1, x2, so they're related to my unknown vector, x. And let's just do the same technique as we did before. Let's pull out their coefficients and put them in a matrix, into the coefficient matrix, right? So the first entry would be 2t followed by e to the t. Next will be 1 over t. And lastly, we have -1. Is that good?
Yep.
Okay, so we're just pulling out these coefficients. Okay, pulling out these coefficients. And put these coefficients into this matrix, right? So, all right, so I have x vector, its derivative equals 2. This will just be my t. P matrix of variable t, x. And over here will just be my f of t, right? F of t. F is the vector again, so put a vector sign on top of it. Where P will be the coefficient matrix, 2t e to the t, 1 over t, -1, and f of t will be a vector containing t squared e to the t. Good so far, guys?
Yep.
One question.
Yes, Milan.
Why is P of t not called vector? And I mean, you
Which
know
one?
what I mean?
P of t?
P of t, yeah.
Ah, because P is not a, let's see, where's my marker? Okay, because P is not only a row vector or a column vector, it is a matrix.
Okay.
Right? This is a 2 by 2 matrix, so you cannot put a vector sign on top of it.
Okay.
While f of t is only a column vector, so you can put an arrow sign on top of it. Everything's good?
I don't really understand how we're able to split the PT from the FT from the equation above. I don't really get why we can do that. And yeah.
Okay, let me see. Martin, let me just, first of all, let's see if I can erase these. Okay. Yep, over here. Okay, so do you understand the left-hand side? Left-hand side is easy, right? X prime.
I totally understand that. And I also agree how we can get the X out of it. I just don't know why we can split it.
Why we can split it? What do you mean you don't understand we can split it? Well, do you agree? First of all, do you agree how we get this coefficient matrix?
Yeah, I understand that.
And you understand this 2t e to the t, 1 over t, -1 times this vector would be the same as this part.
Yes.
And this part, right? And then we isolate these x terms from the t terms, so plus t squared e to the t.
That's the issue that I have.
Okay, let me give you one suggestion. Okay, if you are confused with this, let's just replace this x vector by x1, x2. Okay, let me initiate my pen here. So let's do this. Let me do 2t e to the t and 1 over t, -1, and x1, x2 plus t squared e to the t. If you are just looking at this part, okay, and then after you complete the sum of these two, will you be able to get this 2tx1 plus e to the tx2 plus t squared as the first entry?
The issue that I have is I don't get how we can split it up, like make two matrices out of that. And
make two matrices.
So the right matrix doesn't depend on x. So the left one has x vector. And the rest, the right hand side, it has t squared and e to the t, which is not tied to x vector.
Martin, are you referring to this part, t squared and e to the t?
Yeah, exactly. Just that part.
Okay.
Like the left part, I'm completely fine with it.
Yeah, when we explain it, we said because the t squared e to the t is not related to the unknowns.
Okay.
So you notice that the unknowns you're solving is x1, x2, right? And t squared and e to the t is not related to these two unknowns. So you can separate them. So t squared and e to t wouldn't have anything to do with my vector x.
Okay.
Make sense?
Yep.
Okay. All right. And thank you, Milan.
Yeah.
Okay, let me get rid of. Let's see, can I get these off? Okay. So let's finish the last question on this page, and then we'll be done today. How's that?
Sounds good.
Sounds good.
Okay, go ahead and you take a look at that question, and let's go ahead and try to finish it. Let me see where we're on. So example 9, verify that vector x1 and vector x2 are both solutions to the system x1 prime equals x1, x2 prime equals x1 minus x2. Should that be easy?
Yeah.
Okay, so there are two vectors, right? You gotta make sure that both of these two vectors would be able to satisfy this equation. It's a little bit confusing if I use the notation x1 vector and x2 vector. How about we change their name? Because x1, x1, x2, x2 would somehow duplicate what you see in the system. How about we change their name to U and V? Would that be okay?
Yeah.
Okay. So let vector U be 0 e to the negative t. And vector V be e to the t 1/2 e to the negative t. When you write this, what does that tell you? What is the 0?
X1.
Okay. What's e
And
to the
the
negative t?
x2.
That's x2. Good. Let's first look at the case for U. So U has these two entries. 0 is x1 and x2. E to the negative t is x2. So we'll just need to plug these x1, x2 into the system, right? First equation, obviously, x1 prime, so 0 prime, of course, equal to 0. Check. Second equation is x2 prime. So x2 prime, e to the negative t prime. Is that the same as x1 minus x2? x1 minus x2?
Yeah.
Yeah, derivative will just be negative e to the negative t. Sure, it's the same as negative e to negative t. Check, right?
Mm-hmm.
So that means the vector u, okay, vector u containing these two entries satisfy the system, okay? So vector u is a solution to the system, right? Can you do the same thing for the vector v?
Mm-hmm.
Okay. Did I copy the wrong question, guys?
Oh, okay, doesn't matter.
Yeah,
I
that one.
probably missed a negative sign somewhere. Sorry. Oh, my bad. It is 1/2. Okay, e to the t. Okay, forget about this negative.
So there's no negative.
Or how about we just put negative sign for both? No, that doesn't work. My bad. So let's eliminate this negative sign. Should be 1/2 e to the t. 1/2 e to the t. Now would that work?
Yep.
Right, because if you plug x2 in, so we would have 1/2 e to the t, its derivative, is that the same as e to the t minus 1/2 e to the t? And we know the left-hand side is 1/2 e to the t, right?
Yep.
It is the same as 1/2 e to the t. So yes, equation 1, equation 2, both check, which means, okay, so therefore vector v is also a solution to the system.
Just to make
Yes,
sure,
Milan. Mm-hmm.
if we have 1/2 e to the t, then vector u, the solution for vector u wouldn't be correct, right?
If I had what?
If our vector u of t is okay, it's different x1 and x2 for
Yeah,
you.
vector u is fine. Vector u is
Yeah,
okay because we have
Yeah.
checked both x1 x2 satisfy the system, right? Vector v, there's a typo for me from my side. It's e to the t, and the second entry should be 1/2 e raised to the t, not e raised to negative t. Okay. So if the second entry is 1/2 e to the t, then both equation 1 and equation 2 works. And vector v is also a solution to the system. Make sense, folks?
Yes.
So no questions?
No.
All good. I think all good.
Okay, great. So let's, because it's a Friday today, let's stop earlier, okay?
Yay.
And also we're ahead of our schedule, so we're not in a rush anyway.
Nice.
Perfect.
Okay, so you guys just use your weekend and try to do your test 3, take home.
Yep.
At the same time, I'll post the homework for this week, but I may have a looser requirement for the deadline of this week's assignment.
Woohoo.
Okay?
Thank you.
Yes, thank you.
Okay, thank you guys.
Thank you, Dr. Wu.
Yep, I'm gonna end the meeting. Yeah, you guys, take care. Stay at
Bye.
home. Don't go anywhere.
I'm coming over, Dr. Wu.
No. You know, what did it say? 6 feet? You're gonna keep 6
Yeah, as
feet.
long as we're 6 feet apart, I can be over.
6 feet above. Yes. You're 6 feet apart.
They
All right.
party at Dr. Wu's.
Yeah, party
Have
at
a good
Dr. Wu's. Be there.
All right. Bye.
Bye.
Mm-hmm.
Bye.